Hello guys, good morning and welcome to a new session of TV Liceo. In this occasion, I'm here with you again with this fascinating topic. At least for me, is one of the most fascinating topics in this subject, in physics. And you have made a homework about this. So I think that we're going to do just fine in this session. It's about the Big Bang, as you can read here behind me in the title of this presentation. I don't know, some of the things that you can notice right here, guys, is that I have two images. The first one is a person, right? And the other image that I have here is, can you tell me what it is? What does it look like? Meanwhile, you decide what it is, what it looks like. I'm going to tell you who this person is, who this character that I'm showing you here is. This is nothing less than the father of the universe. Well, not like that. At least the father of the theory of the creation of the universe, which we know as the Big Bang. Okay? Yes, Ana Lisbeth is mentioning that thing, it's bread. Yes, you're right. It's kind of a, if you notice, there is something inside that bread. It is going to be important. We are going to use kind of this as a model, as an analogy of the universe. There are some raisins in this bread, okay? And we're going to go back to that in a moment. So this is why I'm including these images. We are going to use these like some models to describe the universe, okay? But again, about this person that I have right here, this is the creator of the theory of the Big Bang, okay? His name is a little bit long. He has a lot of middle names. The first one is Georges, and the last name, since he is from Belgium, I think it's French there. I don't know how to correctly pronounce the last name. Is Georges Lemaitre or something like that? Georges Lemaitre. Georges. It has kind of other three middle names. It has a long name, okay? But this Georges Lemaitre is the creator, or the one that came up with this idea of the origin of the universe coming from this particularly small atom, and where all the matter of the universe was concentrated there with huge temperature and huge pressure, and everything that we know, the space-time, didn't make any sense at that point, okay, under those conditions. So a little bit something about this incredible person. It's actually was a very, very smart person. He, if you notice, he has this distinctive color. Can you tell me what is distinctive for? What was kind of his profession? What did he dedicate his life to? He liked the bread a lot. Maybe he liked it for some analogies. Yes. So, can you guess what was his occupation from that color? So he's mentioning here, he got to that conclusion because he sees that all the galaxies and planets move so fast in many directions. Good, I see that you made your homework, right? Very good. So, right now what I want you to notice, guys, is that this person, Georges Lemaitre, was, yes, a scientist that came up with this important theory about the universe, but he was also not a baker. He was a priest, okay? He was a Catholic priest, right? So he was into religion. He was a religious person, but he also was a scientist, a very clever, very smart scientist. Actually, he wanted to be a priest since a very young age. From 9 years old, he told to his parents, that he wanted to be, I don't know, at the service of God, being a priest. And also, I don't know, he kept on with this idea. He studied in Catholic schools and all of that. But later, when he was 20 years old, he had to go to the war. He was born in 1894, okay? He was born in the 19th century in 1894. So when he was 20 years old, he had to go to the First World War, and I don't know, that was a devastating experience for him. But something interesting there, guys, that their comrades mentioned something weird about him. That inside of all of that chaos, that was the war, guys. It was the First World War, the First World War, right? He kind of disconnected, had that kind of ability to disconnect from everything else that was happening, and use his free time to study physics, books of physics. He was reading books about physics. So he always kept these two interests, the religion and also the physics, the science and physics. And even in those conditions, which I think is, I don't know, a very curious thing to mention about him. But anyway, later on, he was introduced with the work of Albert Einstein, right? And he knew about the theory of relativity and all of that. And then he tried to complement all of his ideas, what he was studied before, with this idea of the relativity of Einstein. And later on, he came out with this Big Bang theory, okay? That the origin of the universe comes from this single point with immense mass and temperature, then suddenly expanded in all directions, right? And that's kind of a very, very big simplification of that theory, okay? But if you notice also here, guys, we're going to be focusing on the supporting evidence that exists about this theory, okay? And let me just continue with the next one. Okay, since I have told you that he was also in this era or this time where a lot of different scientists were discussing about these things, about the origin of the universe, and as more evidence was being found that supported his theory, he came up with this thought, guys. It says here, in the future, development of quantum theory happens to turn in that direction, or in the direction of his theory, we could conceive the beginning of the universe in the form of a unique atom, the atomic weight of which is the total mass of the universe. I don't know if you can conceive this idea, guys. If you know about the atomic number or the atomic mass, the periodic table of elements, you can see those values. But imagine just a single atom with the atomic weight of the whole mass of the universe. It's kind of a huge thought, a huge idea. So lately in time, guys, with more discoveries, this theory was supported with more findings, okay? And we're going to be focusing, you might know about this already, we're going to be mentioning some of this evidence that supports this theory, okay? For example, we have here an explanation of the redshift. So if you have done your homework already, guys, can you tell me in the comments here in the chat, what is this redshift, okay? I'm going to try to explain it very, very quickly. In this image, guys, in the letter A, you're watching an image of the universe as it began, of our galaxy, right? At the beginning, it was only kind of a cloud of dust and gas and all of that. But at that time also, somewhere else in space, a galaxy had already formed, right? And the light that that galaxy was giving away had this kind of is represented here with that yellow color, okay? So that's the original color of the galaxy. Anyway, the time goes on, right? The time goes on, and as this theory says that the universe is expanding, right? All of the objects in this space are getting farther away. So this light is coming towards us, right? So in the point number, in the letter B, you can see our planet, Earth, in its very early beginnings. It was very volcanic, had a lot of volcanic activity, so there wasn't life yet. In that stage of our planet, that light was kind of in the middle point. It was still traveling. But as you can see, the galaxy is a lot farther away, right? Because the space itself is expanding, okay? So I hope that you remember about these guys, that when a frequency has a very short length, it has a particular color, right? If you change that length of that wave, it's going to give you another color. So if the length increases, it's going to turn to a shade of color more similar to the red, right? To the red spectrum. That's why we see the middle wave in color, in orange color, right? And that change is due to the expansion of space. That light that comes from the galaxy is also distorted for that expansion of the space and changes its color a little bit, as you will see in the image in the middle. Billions of years later, guys, when our planet is as we know it today, that light reaches our planet, okay, and we can detect it. But at this moment, billions of years have passed since the origin of that life, of that light, okay, from the galaxy. As you can see in the point C, the light has already reached the Earth, and we can detect that light, but the frequency has changed. I don't know if you can see it right there. First it was yellow, then the frequency or the length increased because of this expansion of space. So it turned orange, and then increased the universe expanded a little bit more, the space expanded more, and the life within that space expanded also. And that is why we see now the color red. That is a very brief explanation of this evidence, of this theory of the expansion of the universe, the red shift of the light of very distant galaxies, okay? Some of you are mentioning maybe the age of the universe, 13.4. It's kind of very, since these quantities, guys, are so large, some people say, I've seen in literature a lot of different numbers, 13.7, 13.8, 14 billion years. So, but for that scale of that time, guys, give or take a few million years, and it's going to be almost the same thing, okay? Just try to consider the big scale of time and space that we are dealing with when we are talking about the universe. Okay, but yes, very good comments. Now, guys, this is an example of this evidence, or first piece of evidence that is called redshift. If you have encountered that information in your homeworks or something like that, well, it's kind of explained in this example. But now, guys, we saw this example of this galaxy that was, I don't know, maybe 13 billion years away from our planet. What about things that were beyond that galaxy, that were a lot farther away? What do you think it would happen to the light? The electromagnetic spectrum ends with the red? What else is after the red? I don't know if you remember also this image, guys. We saw it before when we were learning about waves. So the visible spectrum is very, very short, right? The electromagnetic spectrum that we are able to see is very, very limited. It goes from the red to the violet, okay? After the violet, you have the ultraviolet that are not visible anymore for us. And below the infrared, below the red, we have the infrared, and then the microwave, and then the radio signals and all of that, okay? But we cannot longer see those because we are not done for that, right? Our eyes can only have a very definite range of visibility. So, if another galaxy was farther away, guys, and had experienced this process of red shifting, what do you think is going to happen with those waves? I'm going to make a little demonstration here, guys. This is I don't know if you can see it very well. I think I'm going to have to go closer to the camera. Just, I don't know where should I show it. Let me see. I have a hard time with showing this because since there is this lag in the image, more to the right, to the left, to the, where? I'm going to the right, but I don't know if, no, to the left, okay. I'm sorry about it, guys. Okay, what I'm representing here, guys, I think we can see it right there, right? What I'm representing right here is a specific wavelength, right? Think of the balloon that I'm holding here as the space, okay? You're right, you're the left, now more to the other left. Okay, I think that we're already there. So I try to draw a wave right here, guys. Think of the balloon as the space in the universe, okay? So if the universe is expanding, what do you think is going to happen to the wavelength of this wave? I'm going to do it right here, okay? We have a certain frequency, a certain wavelength there. And let's see what happens when I stretch it. I hope I don't hurt my fingers. So you see, what happens to the wave? This is actually what is happening to the light from that is coming from all of these distant galaxies and stars, right? And thank you for that camera effect. What I wanted to show you here, guys, in this image now of the electromagnetic spectrum is that the more the universe expands, right, the more these waves are going to redshift, okay? And they are going to go beyond the red, right? They are actually in the microwave zone. So it has expanded that much, right? This wave that is now in the range of the microwaves. And this gives us another piece of evidence of the accuracy of the of that this theory must be true. I'm talking about the cosmic background radiation. So this is a picture of that, guys, precisely that. All the telescopes that have been used for this purpose, when they point to any direction, either if it's daytime or nighttime, they can perceive this background radiation, cosmic microwave background radiation, right? They can detect it everywhere from every direction in the universe, okay? Yes, it's a radiation, Hernan, and it's a form of an electromagnetic wave, okay? So it's radio microwaves, okay? So from all the places of the universe, we can detect this radiation, this background radiation. So since it's in the scale of the microwaves, guys, this light or this radiation has redshifted a lot, which means that it's at a huge distance, right? And it's very, very old. If you go back in time from this point, that's how you get this number of 13.7, 13.8 billion years, which is the age of the universe, the estimated age of the universe, according to this Big Bang theory, okay? So we have discussed these two very important pieces of information, but this wouldn't have been possible without the help of some other scientists. I'm going to mention some other, you have heard about it, I'm sure. You have heard about him. It's Edwin Hubble, right? The very famous telescope that has his name. I think is very, very well known. So Edwin Hubble used a lot of other different telescopes here from Earth to observe the stars, the different distance stars. So 100 years ago, guys, all of the lights that we used to see or that people used to see in the sky, they thought that they were inside our own galaxy, right? They started observing these accumulations of stars, but they thought that they were inside of our own galaxy. But Hubble made these discoveries that, in fact, these accumulations of stars were very, very far away from our own galaxy. They were other galaxies, okay? And he found a way to calculate the distance and even the speed at which these other galaxies were moving far away from our planet or from our own galaxy. And this is something very, very curious here, guys, because before this person, Edwin Hubble, came up with this, it is called the Hubble law, or the law of Hubble, which measures the velocity of the galaxies. There was other person which came out first with the same law, with the same theory about the velocity of the different galaxies, and it was nothing else than the father of the Big Bang theory. So this person also, Georges Lemaitre, came out first with this law that is attributed to Hubble. The thing that happened here is that yes, Lemaitre published his results, but he published in a Belgian journal which didn't have a lot of popularity. And some years after that, independently, Hubble came to the same conclusions, and he published his findings in an American journal which had a lot of diffusion, and so it was attributed to Hubble. But anyway, after that, Georges Lemaitre find out, and he said, it's okay, I don't mind. I discovered that first, but anyway, you can have it. I think that he was thinking, since I'm the father of the universe, you can have whatever you want. But anyway, some other piece of evidence, guys, is precisely that the galaxies are getting farther away from each other, okay? And that's why I used this example. I don't know if you like cooking, if you like bread. This bread has raisins in it, but this is an example of the universe. In order for us to understand how these different galaxies are getting away from each other, think about each of these raisins inside the bread as a galaxy. And when this bread is, I don't know, is cooking in the oven, it is rising, right? Little by little. And all of this, from the point of view of each of these raisins, every other raisin is separating away from them, from each other, right? So there is no specific center, there is no, that is kind of very weird to think about. So the universe doesn't have any center because everything is expanding away, right? At the same rate, see, from each other, from each galaxy from each other. So I think this is a very, very interesting model, guys. And also, if you can see the background image, guys, of these galaxies is kind of a representation of how that is happening, okay? A very important observations to make right here, guys, is that the farther away a galaxy is, the greater is going to be its speed, its velocity, okay? That is also explained by this Hubble's law. And I don't know, this is only some other piece of evidence to show that this theory is right, or is very close to the truth, no? Or what happened before in the Big Bang. It's very, very interesting and fascinating in from my point of view. I don't know. So what is going to be next, guys, I would like to try to do an activity. For this activity, you will have to access to a document, which if you please, Oscar, do me that favor. We are going to share the link for this document, guys, in the chat of the TV Liceo session. And we're going to do something, okay? We're going to try to replicate that experiment of the expansion of the universe with this other balloon that I have right here, okay? So in this document, guys, you're going to find a table. You're going to find a table in which we are going to be introducing several data, right, that we are going to obtain right here. Okay, so if you notice, with this other balloon, I'm also going to be representing the universe. And I don't know if you can show the image of the galaxies. We are going to try to represent some galaxies. I included some images here of different galaxies, guys, so just so you know their names and how they look like. First, we're going to start with our own galaxy, okay? In this representation of the universe that I have here in this balloon, I'm going to put very close here our own galaxy, the Milky Way, okay? And then I'm going to draw Andromeda, and then I'm going to draw the pinwheel. Then I'm going to draw the Sombrero Galaxy, then the Whirlpool Galaxy, and at the end, this Tadpole Galaxy, okay? I'm going to draw them in that order because they are in that sequence farther away from the Milky Way, okay? So Andromeda is closer than the pinwheel, and the farthest galaxy is the Tadpole Galaxy, okay? So if you didn't know this, how they look like, so you have a very good view right there. And I'm going to tell you what we're going to do, okay? I'm going to inflate a little bit this balloon. Then I'm going to start measuring the distance from the first one, which is our Milky Way, our galaxy, to the second one, to the third one, etc., etc. And you are going to help me to register these measurements in that document, okay? So we're going to measure an initial distance, and then when I inflate it a little bit more, we're going to measure that distance also, okay? I have my ruler right here, so I'm going to give you that result, and you're going to register that information in that table, okay? So for the first column, guys, which says initial distance, I'm going to inflate this one. I will have to remove this for a moment. Don't worry, Oscar is very far away, so it's okay. Think a little bit. I don't know if you can see it. I'm going to try to show this again right here, but I have drawn this. Can I see them there? Oh, because of the light, maybe it's going to be very difficult, but I don't know if you can tell that there are the different galaxies. Oh my God, I never get this take. So there are the different galaxies, kind of a representation over there. And I'm going to be measuring the point to those different galaxies, okay? So the initial distance from A to B, which is from the Milky Way to Andromeda, is going to be 2 centimeters. So number 2 for the first cell. From the Milky Way to okay, I'm sorry, it deflated a little bit, so I'm going to change that. So from the first point is going to be 1 centimeter, okay? From the Milky Way, from A to B, 1 centimeter. From A to C, it's going to be 2 centimeters, okay? The second cell. From A to D, it's going to be 3.5. Okay, I need you to take note of these results, guys. Can you do it, please? I'm going to repeat the first one. From A to B is 1 centimeter. From B to C, 2 centimeters. From C to D, 3.5. Okay, so can you help me registering that? Those values there in the document, guys, please. Before I forget about them. So it's going to be 1 for A to B, 2 for B to C, and 3.5 from C to D. Okay? So before we move on, guys, I need you to include those results there. (3.5) to C to D. Then it's difficult, this one. 4 centimeters. The next one. Okay, are you ready for this, guys? I see some of you are in the document, but I don't know if you forgot. Yes, thank you. 2 centimeters from B to C, 3.5 from C to D. The first one was 1 centimeter, okay? Thank you. And from D to E, it was 1, 2, 3, 4, 3.5. It was 4 centimeters, okay? From D to E, 4 centimeters. And the last one is going to be 5 centimeters, okay? So 1, 2, 3.5, 4, and 5. Now, what is going to happen is that I'm going to expand the space of the universe. I'm going to blow as hard as my lungs allow it. So, let's check what happens. Okay, right here I'm going to be measuring the distances again. From A to B is 3.5. That distance is going to be in the first column of the first expansion that says distance, right? Okay, let's make it 4, okay, in order for us to have close numbers. 4 for the first column, 4 centimeters. For the second one is going to be 5 centimeters. For the third one is going to be 9 centimeters. So 4, 5, 9. And the next one is 14. Okay, in the first one, it's 3.5, okay? The ones that says distance in centimeters in the first expansion, that should be 4 instead 3.5, okay? So 4. The next one is going to be 5. From C to D is going to be 9. From D to E is going to be 11. I don't know if you're following these guys. I don't see the numbers there. 4, then 5, the second, yes. The third one is going to be 9 centimeters. Yes, after the 5 is 9 centimeters, and after that is going to be 11 centimeters. And the last one is going to be 14. Okay, 11 and 14, that's the last one. So if we make here this difference, guys, so from 1 to 4, we have a value of 3, okay? 3 centimeters. If we are going to consider this expansion, we're going to give it a similar time, and we're going to consider a time of 1 second, okay? So the difference is going to be 3 centimeters for the first one. The difference is also going to be 3 centimeters. I'm going to write it here. 3 for this one. The difference from 2 to 5 is 3 also. From 3.5 to 9 is 5.5, I guess. Right? From 11 to 4 is 7, and from 5 to 14 is 9. Okay, so if we transform this information, guys, into speed, we're going to find that the first galaxy, Andromeda, a representation of Andromeda, is moving at a speed of 3 centimeters per second, okay? We're using a way smaller scale than that compared to the universe, just to understand this concept, okay? 3 centimeters per second, which is also going to be the same of the second galaxy, 3 centimeters per second. But what happened with the third one? Now we have a speed of 5.5 centimeters per second, and the one that is farther away has a speed of 7 centimeters per second, and the farthest away has even greater speed, okay? 9 centimeters per second, okay? If we repeat this process, guys, if I inflate this one again and we measure again these distances, we're gonna find out that the speed is increasing the farther away you are from your point of origin, okay? So this is kind of a very simple demonstration of how the universe is expanding and how the galaxies are expanding or are being carried away in this expansion of space. Right? So maybe we can check this experiment a little bit better in classes, guys. I want to conclude this experiment right here. I hope that you like these different examples, guys, and that's going to be it for today, guys. So thank you for your participation. I'll see you in class. Goodbye, guys.